Undo. Okay, given an array nums of unique integers, return all possible permutations. You may return the answer in any order. Now, 1, 2, and 3, cool. 1, 3, and 2, cool. 2, 1, and 3, cool. 2, 3, and 1, cool. 3, 1, and 2, cool. And 3, 2, and 1, cool. So, in this, the problem is the ordering. So it's not necessarily just removing the value, it's the ordering of the values. You know, when the length reaches 3, that's when you know to go back, maybe backtrack. Actually, how would you go about this? So you look at the first value in the nums array. The first value is 1. You put that down, and you say there are 2 choices that you can choose between, 2 or 3. And you would say, okay, 2 comes first or 3 comes first. And then from the remaining in the backtrack, what do you have? You have 3 and 2. When the list becomes empty, you know that is an option that you will add to the resulting list. And you would keep on backtracking up, and then you realize, okay, at the very first position, you can say, you can choose 1, or you can choose 2, or you can choose 3 to begin with, and then the rest is history. Okay, I can kind of see how this could be a backtracking problem. We're going to return the result. We're going to say this is a definition of a DFS problem. This is going to be return some value. We're going to DFS again internally twice. Well, actually, it's going to be DFS'd within a for loop, so that's something to consider. The input will say we take a nums. Alright, so the nums here is what's really going to make a difference. The nums DFS now depends. So for n in nums, I guess, or let's just say for I in nums. Now this is going to be the len of nums. Going to be the range len of nums. I nums I is it going to be +1? If you start from 0, right? If you start from 0, you want to say go to the 1 DFS. And you want to say actually, this isn't the right way that I was. I don't think this is the right iterations that I have to do here. You're going through each of the nums. That's the thing. You're going through each of the nums. And you're adding these nums with something else. So this is going to be, I guess, I could say index, I guess. I can say index, I think. And maybe make this j. Maybe j. But nums of I. Nah. I gotta actually make this nums of j. And make this equivalent to an actual num. If I make that an actual num, then this num is added to some construction. So constructor, I'm going to say it's some constructor dot append num, and at some point you're going to have to constructor dot pop num, or pop. Alright, I'm just going to pop that value off the top because you're doing this in a DFS manner. So when you append that though, if the result, if nums is, so if len of result is equal to len of nums, then you, so okay, constructor, sorry. Constructor, if len of constructor is equal to len of nums, constructor res dot append constructor res dot append constructor copy. Okay. And DFS of nums j. Now we can probably just call it I again. Nums I with nums decrementing Now the problem is we're going to have some issues. Damn, that's we're gonna have some issues. Let me think. There are some problems just me looking at this. There are many problems when I just look at this. I don't know, you have a constructor, you append the number to it, and then you would add that number only if this is true. Now, each of the remaining numbers in nums we do a DFS of this and nums I. Now it's not nums I, is it? Because it'll have to be it just has to be that num with that removed. Can I make it so it's not removed like that? Num and nums. Now let me be straight with what nums is here and what num is. So num is the value that you want to add to the result. Nums is the remaining values that are left to be added. Now, does that mean that you really need num Because here's the thing, right? You want to return, so you want to do a DFS of nums. And that's basically all you want to do. So I don't think it makes sense to put that there. But if it doesn't make sense to put that there, it means that these have to be moved. Possibly, perhaps, inside here. So that these are indented. So in the DFS, you're doing a for loop. For whatever's remaining in nums, you have a constructor where you add the num. Now the num here is just nums I. And then if len constructor is equal to len of nums, res append constructor copy. Now it's not len of nums anymore. Equal to n. Well, technically you can say if instead of len of nums, if ci, change this. Whoa. Okay, whoops. Change. Yo, why is that highlighted like that? Actually, kind of sus. It's kind of bugged out there. Okay, if nums is equal to just an empty set. Right, that's the base case. But if it isn't, you would append that, and you would do a DFS. Of the remaining nums. Sorry, you would do the DFS of the that remaining nums. You kind of want to do nums excluding whatever is in nums. Next level CPP. Look up for swaps. Every time you swap different elements to get a new combination. Every time you swap different elements to get a new combination. Yeah, I can see that as a way. I'm thinking of it a different way. But we'll probably end up doing it your way eventually, probably if that's the right way. We're going to do everything else excluding this value. Okay, so I'm going to say it's going to be nums Let me think. So nums, so I want to weigh, so this is, if I is 0, or what if I is 1? So up to 0, plus equal, or plus nums I plus 1. Is that good? Assuming I plus 1, that's okay, so I don't know whether you can do this, so I'm gonna just check. So if you're given an array, right, that's equal to 0, 1, 2, 3, and you have what's array of, so let's say I is equal to 0. Now array of I, that's going to equal to 0, 1, 2, 3. When you have array of I plus 1, 2, and you slice it like this, that should be an index error? No, so it'll be from I plus 1, so it's going to be 1, 2, 3. But now what if your I is equal to 3? Your I is equal to 3, you have 3, or you have nothing, I'm guessing. Good, okay, so nothing is good. This is what we need, so that should work. Partially. Okay. Yeah, we got it. Let's go! Alright, that was good. That was good, that was good. We figured it out without even looking at the solutions. So I'm happy with that. But let's look at the reasons here. Okay, now it doesn't even look like we use a, doesn't even look like we use the DFS at all. Am I right? Is that? That's interesting.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem permutations. I've actually already solved this
Next level
before,
CPP.
but I think I could explain it a bit better, so I wanted to do it again. We're given an array of distinct integers.
You do Leetcode in CPP? Yeah.
Possible permutations
I do it in
those
Python.
So for the record, a permutation of a set of numbers like this would look something like this. We have 3 numbers, so we're going to have 3 positions to fill. For the first position, we have 3 choices. We can pick any of these 3 elements. So let's put a 3 over here. For the second position, we don't know which element we already picked. We could have picked this one or this one or this one for the first spot. But either way, we know we're going to have only 2 elements remaining.
Yeah, Leetcode is good.
To place over here. So there's going to be 2 different elements that go here. And then after we've picked the first 2 elements, this one is already decided. So we'll put a 1 here. So 3 times 2 times 1, we'll have 6 different permutations of this set of numbers. And in order to visualize it, let's kind of draw a decision tree. So let's say that for the first choice, we can choose among 3 elements. We can have 1, 2, or 3. So regardless of which path we take, we're going to have 2 choices. Here we can have either a 2 or a 3. We can't have a 1 because we already picked it. Here we can have a 1 or a 3 because we can't have 2. We already picked it. Here we can have a 1 or a 2, but not a 3. So now it's going to get a bit more simple. We'll only have 1 choice for each of these, and it must be the element we haven't chosen. So here it's going to be 3, here it's going to be 2, here it's going to be 3, here it's going to be 1, here we haven't chosen 2, and here we haven't chosen 1. So now, if you go through each path, we have a permutation. We have exactly 6 of them, and you can see every single one of these is different. So if we could have each of these in an array, this is the result. Like, we've calculated the entire result. Now, the only problem with the way we're thinking about it here is it's pretty easy on like pen and paper to draw this out, but how would we actually calculate this in terms of code? Obviously, it looks like we're using recursion, and it's definitely possible to do it that way, but the way we're doing it right now involves a decent amount of bookkeeping. Because what exactly is the subproblem? Like here, we chose 1, right? So we got rid of 1, and these are the elements remaining. So now we're trying to create permutations with those elements.
Wait.
But here,
Okay.
the subproblem is different.
Oh, he does
Here
do
we used
DFS.
2, so now we have these elements remaining, and we're trying to create permutations with those elements. Again, we could do it this way, but it would involve like removing this element and doing some other stuff. So I think a slightly easier way to think about this problem is to really use the idea of subproblems, because it makes recursion very, very easy. So let me kind of redo this in a very simple way. Now we're still gonna use recursion, but we're actually not even gonna branch anywhere. So you're gonna see something interesting. Here, we have 3 numbers to choose from. So what we're trying to do is give me all permutations from 1, 2, and 3. But next, the subproblem we're...
I just remembered I had a tool that I could use to draw as well. Because I'm looking at the way he's drawing things, and I do have something similar, but where did I put that? It's called a Wacom tablet, but I'm trying to remember where I put that. Oh, wait, is it right here? No. Or did I sell it? Wait, did I sell it? Damn, I shouldn't have sold it. I sold it on the like a market. Damn, wait, did I really sell it? Do I regret that? Man, it's alright. Yeah, I think I did sell it. I never thought about it until now. It's been like 4 years. It probably was never going to be used anyway.
Ask is this. Give me all permutations with just these 2 numbers. So we're going to have something like this, 2, 3. And then finally, we're going to ask, just give me all permutations with just a single number. Notice how it's getting more simple as we go down. So watch what the return value is going to be.
Yeah,
well,
next level
let's go to the
CPP.
base
If I
case.
really
don't
needed
have
it, I'll
any
buy a new one.
elements. From here, I'm going to return up an array with an empty list. Like, that's our permutation. We can only create 1 permutation with an empty set of numbers, and it's an empty permutation. So that's the base case, just to keep it simple. And now it's going to stay pretty simple. With just 3, how many permutations
I'm going to
do we
stand.
have? Well, it would look like this. We're going to return up to the parent just a single array with the value 3, because a single number can only be permutated like that. Now it's going to get more interesting. From here now, from this subproblem 2 and 3, how do we solve it? Well, you probably know what the return value is going to look like. It's going to look pretty simple, just like this. So it's going to have 2 in the front, and it's going to have 2 in the back. So 3, 2, like this. So these are the 2 permutations we can create. Now, the reason I'm showing you this way is so easy to calculate. Just watch this. From the base case, all we do is just add 3 to that list. Okay. Now, from here, this was the numbers we're given. We already got all permutations from 3, so now the only thing to do is to add 2. So what we do now with this array, it's a very simple array. It just has 1 element. So we know we have 2 choices, actually. With 2, we can put it at the front, or we can put it at the back. So that's exactly what we do. We create a permutation with 2 at the front, and then we create a permutation with 2 at the back. And then from here, we're going to do the same thing. We have these 2 permutations, 2 and 3. What we're going to do is try to put 1 in every position. We're going to try to put 1 at the beginning. We're going to try to put 1 in the middle. And we're going to try to put 1 at the end. So we're going to end up with 3 different permutations. We're going to do the same thing. This one, we also have 3.
His brain is more
2.
flexible than
It's
mine.
obviously different from 2, 3. So we're going to put 1 at the beginning, in the middle, and at the end. And if we do this, we're going to end up with 3 more permutations, which is 6 total permutations.
Because I thought of it more formulaic.
And if you're curious, I'll quickly draw out
This
those
is more
permutations.
creative,
Here
I would
one
say.
goes at the end. Here one goes in the middle. When I said end, I meant beginning, sorry. Here one goes at the end. And from this permutation, 3, 2, we're going to put 1 at the beginning, so 1, 3, 2. We're going to put 1 in the middle, 3, 1, 2, and we're going to put 1 at the end, 3, 2, 1. These are the 6 permutations. Now let's code it up, and I'll also explain the time complexity in the coding solution. So we're going to start with the base case, which is pretty simple in our case. We're going to have the length of the input, and when it's equal to 0, we're going to return a list with a single empty list inside of it. And so the reason we're using that is because we're only going to have a single parameter, the input list. The idea is that we're going to keep calling the recursive function with the input nums without the first element. So that's the sub problem. Just get rid of the first element from nums, just create a subarray starting at index 1, and that'll give us all the values from nums except the first one. So these are our permutations, like our subproblem, and then we want to, from these, add the current element, which is the number at index 0, to all of these in every possible position. And we're going to store those in another variable, which I'm going to call result. That's what we're going to end up returning from this function. Now to actually do what I said earlier, let's just go through every single permutation that we have. And for each permutation, let's go through every possible index that we could insert the current value into that permutation. So I'm going to get the length of p. I'm also going to have +1 because we technically could add to the end of the permutation as well. So now for that permutation p, I'm actually going to create a copy of it because we're going to use this one multiple times. We're going to possibly add a value to it in multiple different places. We don't want to modify the original permutation. We just want to create a copy of it. So I'm going to store that in a variable called pcopy. Then for pcopy,
so let me understand this.
Index I,
you're telling me that pcopy here is from permute, which could return a list of lists. So this is a list here. This is a list copied.
Value nums at index 0. We're taking this value, inserting it at this index. We're going to do that for every index.
Yeah.
And then we're going to take pcopy and append it to the result.
Yeah.
We're going to do that for every permutation, and then the result is going to be here, and then we're just going to go ahead and return. Now, as you can see on the left, this solution works, and it is very efficient. Well, it's about as efficient as we can get for this problem. And let me just kind of show you how to analyze the time complexity. The idea here is it's going to be easier for us to do it without kind of focusing too much on the code. Remember that how many...
All right, let me think of my time complexity here. Because we're doing a DFS on the different branches, you know, it starts off with, you know, the branching factor slowly decrementing, but by 1 every level deep. So given nums, it's almost as if it's 2 factorial. I mean nums factorial. Is it not just nums factorial? Because it's a permutation anyway.
How many permutations are we going to have? Well, if we have 3 elements, we had something like 3 times 2 times 1. That is a math equation called n factorial. So if we have n elements in the input, we're going to have this many different permutations. How do we build each individual permutation? Well, to add a single element to a permutation, we're like inserting in the middle. That's how we're coding this up. So it's an n operation, and that's just inserting 1 element into a existing permutation. If we're inserting n elements into each permutation.
So unlike the most of backtracking questions, this question is O of n factorial, not O of 2 to the power of n. because every number can go any index. It's not a binary choice anymore. Yeah, I agree. So yeah, that's a good, yeah, I did say n factorial, so perfect analysis. All right.
We're going to have like an n squared over here.
Let me, wait,
We're,
so
like,
he says
inserting
n
it.
times
That's how we're coding this up. So it's
n
an
factorial.
n operation, and that's just inserting one element into a existing permutation. If we're inserting n elements into each permutation, we're going to have like an n squared over here. So the overall time complexity is going to be n factorial times n squared, but this is really the dominating factor in the time complexity, n factorial. Space complexity wise, if you're not counting the output, which is just going to be n times n factorial, because each permutation is going to be of length n, and we're going to have this many of them. If you're not counting the output and you're just counting like extra space here, the space is still actually going to be n factorial times n, because we have multiple copies of it here. So this is space, this is time.
So I mean, next level CPP, that's I'm literally just going to write what you said. So I will literally just copy what you wrote, and just reference you, to be honest, because that's a good way to express things. So thank you for your input. Perfect.
Don't even branch in this recursion. Isn't it possible to solve this problem without recursion? And you're exactly right. The logic is going to actually be very, very similar. Like, we're going to start
so he's going to try and think of it iterative.
Space complexity is going to be the exact same, so I guess I'll leave this here. But this, we're going to call this our permutations, and we're going to get rid of this because we're not going to have any recursion. I want to leave this code here because I want to show you how similar the solution is going to be. Remember, this is the base case. We want to compute like the subproblem. So for every number, I could use like an index I to make it more clear, but we don't need to. I'm just going to go for n in nums. For every number, we want to now add this number to all the existing permutations. That's what we're trying to do. That's the logic behind this. So I'm going to call the new permutations we create with this number,
new perms.
It's going to be just an empty list for now. We're going to go through every existing permutation, kind of like we did down here, right? Going through every permutation. And now I want to insert this element into every permutation, and I need to do that for every position. So I'm going to say for I in range length of p plus 1, exactly the same as we did down here. And now to that permutation, I want to create a copy of it just like we did before, and then I want to insert into that copy the current element. At index I, we want to add n, so this is slightly different, I guess. It's not nums of 0, it's n. And also, I want to say, let's take this now and add it to new perms. So new permutations, append p copy. The only difference here is going to be at the end, we want to update perms to be this now. So we're going to set permutations equal to the new permutations. And then at the end, we're going to return the permutations. So you can see that the code above is very similar to the code below.
I agree.
And I kind of got rid of the base case here, so this is not like the complete code, but you can see that this portion of the code.
I guess it's cool that I'm looking at this problem
down here, and I'm going to run
not iterative anymore,
and show you here that it also works, and it's also just as efficient for you in terms of big O at least. If you found this helpful, check out Leetcode.
So the thing is, like, with these problems, like if I were to do this permutations problem when I first started, why is everyone getting beats 100% now? Is it really just faster? Like, what happened to Leetcode? I mean Leetcode. Not even telling me anything useful now. What was I saying before? Doesn't matter. It's broken, you think? Yeah. I'm sure you're experiencing the same thing. Okay, yes. Paste. Here we go. Oh yeah, so what I was saying was that when I'm doing these Leetcode problems, like say this permutations problem, if I first, were to get into Leetcode and I did permutations 46, I probably wouldn't be able to solve this in a DFS way or really understand how to do this in a backtracking approach. But, I would have done this problem iteratively, just like what Leetcode would have done there. So it's really interesting that I'm able to now, like this is a sign of progress, that I'm able to now do this permutations problem, not instinctively thinking that it's going to be an iterative approach. So that's still good, even if the iterative approach is the same complexity. Solved without help. Watched video solution to understand iterative and recursive approaches through Leetcode. Okay, and this is Leetcode also explains the iterative approach, which is something that I would have done if I hadn't known / learnt about backtracking in the first place. So it's good that I learnt about backtracking to be able to solve this problem the way I did. So I'm happy with that. And one of the key things from the solution I created was the use of a constructor, and which I take a copy of every time. And it's just about the way you think about the problem and then just solving it the way you want it to be solved. Palindrome partitioning is a good backtracking question to you too. You can try it. I'll get to it. The problem is we're going to call it a day for now. But okay, yeah, palindrome partitioning. It's going to be in an upcoming Leetcode problem anyway. So Leetcode problem anyway. So I'll do it then when I get to it. But yeah, perfect.